All right, compound interest, i.e. financial applications of logarithms and exponentials. So as we get into this application section, there's kind of like three big categories of applications of logarithms and exponentials. That's not to say that there aren't other categories. I would just say in general, there's like three big ones. There's finance, which is going to be compounding interest. There is biology for population growth and decline. And then there is chemistry for radioactive decay. We're going to cover those sections. That's what we're going to do here. So we're going to start here in this compound interest section by talking about the financial application of logarithms and exponentials. For this section, there are two really big formulas. There's the compound interest formula, where you compound a certain number of times each year. That's going to be this formula here, and I will break it down, don't worry. And then there is continuous compounding interest formula. This is this like A equals PERT thing. A equals P times E to the RT. This formula is going to get repeated in every single section. It's like the same formula used in different ways. Again, we'll get to that. Let's start with this guy up here, our compound interest formula. Let's talk about all these pieces here. So we have A equals P times 1 plus R over N raised to the NT. What do any of those mean? All right. So first of all, A. I like to think of A as like amount. So it's the amount after T years. It's your accumulated value, if you will. Your accumulated value. So that's how much you'll have in your account that has a certain interest rate after a certain number of years. This P out front is principal. What did it do? P is equal to principal. And that's not principal, but principal. That's the amount initially invested. How much did you invest into your savings account at the get-go? And I'm going to give myself more room here. There we go. Sometimes this is also called present value. So the present value of an amount that could become this amount after a certain amount of time is the idea. All right. R is the interest rate given as a decimal. So you do need to know how to turn decimals into percentages, or percentages into decimals, really. Both ways are important. But R is the interest rate as a decimal. Interest rate as a decimal. N is the number of times per year that the account compounds. Okay, so I just I just went to look up something and I realized, oh, this is so silly. I did spell principal wrong. I feel like I've checked it 1.5 million different times because I've been teaching this for 10 years now. And somehow I still managed to spell it wrong and then act so confident about it. How dare I? I hope somebody sends me an angry email because they didn't watch this part of the video and they thought I spelled principal wrong. How did nobody call me out on that? I've taught this so many times and I've probably been spelling it wrong the entire time so confidently. Anyway, principal is spelled with a pal. It is your pal, I guess. Who knows when I got that wrong? Anyway, n is the number of times per year that your account compounds. And what that means is that the interest you earn is added to the principal. The interest you earn is added to the principal, and then when the interest gets recalculated for the next compounding period, you are getting interest on top of your interest because your interest that you got in the previous compounding period has been added to your principal, so your principal is now larger. What that means is the more times per year that we compound, the more we're going to get back on our investment. You want to compound as many times as possible per year. You will get more money that way because you are adding more money to your principal, which is spelled PAL, I guess. N is the number of times per year that it compounds. So here are the really common ones. If you compound annually, that means you're only compounding once a year. If you compound semi-annually, that is twice a year. Quarterly is compounding 4 times a year, so N would be 4. Compounding monthly means you compound 12 times a year. Compounding weekly is 52 times a year, and daily is 365 times a year. And you know, it's sort of, except for leap years, but we're not going there, right? Not going there. All right, then there's this here. I said the more you compound, the more money you make. So obviously you want to compound as many times as possible. It sounds like 365 should be the most, right? It's not. Actually, continuously compounding every single moment, always compounding. All right, and it has a lot of the same things as we have up here. In fact, the only difference is that here there's no n value. Everything else is the same. So I can just like highlight this stuff right here, bam, duplicate it, put that right here, and it is the same idea. Accumulated value. This is still the principal spelled the correct way and not the incorrect way. The interest rate is still the interest rate. Oh, and then I also forgot to mention that T is time. T equals time in years. Okay, so these are the different formulas that we use to compute how much money we'll have in our account after a certain amount of time based on our interest rate, based on how it compounds. Let's do some problems with it. So first example, find the amount that results from investing $300 in an account that yields 7.25% interest per year, compounded monthly, after a period of 10 years. Round your answer to the nearest cent. First of all, the most important thing is what formula are we using? And because it says compounded monthly, that means we're using the first formula. Otherwise, it's going to say compounding continuously. But this guy right here means we're using the formula A equals P times 1 plus R over N raised to the NT. That's the formula we'll be using. Up here, we are initially investing $300. So that is our principal investment. Our P is equal to 300. I'm actually going to make this black. We are making 7.25% interest. As a decimal, that is 0.0725. You move the decimal place over twice to the left. We have P, we have R, we need N and T. Because we are compounded monthly, that means N is 12. We compound 12 times a year. And we are doing this for 10 years. So our time is 10. That is all the pieces we need to fill in this formula. So we have A equal to, our principal is 300. 1 plus R is 0.0725 divided by 12. That's our N value, raised to the 12 times 10. Now, I really, really want you, please, if you're listening to me right now, if you are listening to this video and you care at all, put this in your calculator and make sure you get the same thing as me, because if you don't, then you don't know how to put it in the calculator. And you might think that that's a silly thing, right? It's silly to like, oh, of course I know how to put something in a calculator as long as I can get to this far. It's not okay. Listen, calculators are finicky. They do weird things and you got to get comfortable with them somehow. So please plug this in. Make sure you get the number I get. The number that I get when I plug this into my calculator is 618 point. It says to round to the nearest cent. That is going to be 2 decimal places. So 0.7. So there is $618.07 in our account after 10 years if we invest $300 at a 7.25% interest rate. All right. Let's do another example. Jerome will be buying a used car for $15,000 in 3 years. How much money should he ask his parents for now so that if he invests at 8.25% compounded continuously, he will have enough to buy the car? Round your answer to the nearest cent. All right, first things first, we see this word compounded continuously. And that means that we're using the PERT formula. P e to the RT. That is the formula we will be using. So we need P, R, T, A. We need 3 of those 4. We have A, P, R, and T. We need 3 of those 4 things. Up here, buying a used car for $15,000 in 3 years. So this isn't how much he has now. This is how much he hopes to have. He hopes to have. That's our A. This is the accumulated amount we're hoping for. So A is equal to $15,000. 3 years from now. So T is equal to 3. I now have 2 out of the 4. I just need 1 more. And look, it's right here. 8.25% interest as a decimal is 0.0825. I now have 3 pieces of information. I'm going to plug them on in here. So we have 15,000 is equal to, I don't know what the principal is, right? How much does he need to put in now to buy the car? So we don't know what P is. We're going to be solving for P. The interest rate is 0.0825, which, by the way, if you could ever find that interest rate, jump on that and put your entire life savings in it. I mean, I guess unless you're a really good investor and can get better than 8.25%, but not me. All right. So here we go. We plugged everything in. Now we need to solve for P. So I'm going to start by simplifying this exponent up here. And we get 15,000 equals P. E raised to the, if you multiply 0.0825 by 3, you'll get 0.0825. 0.2475. All right. To solve for P, we need to get P by itself. If I had something different here, if I showed you instead, where can I write this? Off to the side here. If I showed you 15,000 is equal to P times 15, and I asked you to solve for P, you would have no problem. You'd say, I'm dividing both sides by 15. I now have 1,000 equal to P. Good, I'm done. Right? There would be no problem if you saw this as a number. But it is a number. It is simply a number. E raised to the whatever, you can plug it right into your calculator. It'll shoot out a number. So to get P by itself, I just need to divide both sides by this number, just like I would if this number were 15. So those cancel. We get P is equal to 15,000 divided by E raised to the 0.2475. If we plug that bad boy into our calculator, which I changed this number from the last time I did it, so I have to recalculate it. That looks good. 11,711. And we're rounding to the nearest cent, so 0.25. So $11,000, 11,711.25. That is how much money Jerome needs to ask his parents for if he wants to buy a $15,000 car in 3 years, and he found a place that was giving him 8.25% compounded continuously. We ask ourselves, does this answer make sense? And I think it does. It's not like we're gaining an absurd amount of interest. So that sounds right. Like 11,000 to 15,000 isn't a ton. This number is smaller than this number, which is important because your principal should always be smaller than your accumulated amount. Otherwise, you're losing money. So you can kind of look at this number and feel like, okay, it feels good. It feels good. Okay. Let's do another example. Making a point here, by the way, this first one right here, this one was solving for an accumulated amount. Just in case like you're looking back through your notes later and you're trying to figure out like which examples we're solving for what. So this one was solving for an accumulated amount. This is solving for principal. An AL. I'm so embarrassed. I literally just taught this section today to a different class and made a big point about that. Principal. Solving for principal. All right. Example. $15,000 is invested in an account that yields 5% interest per year. After how many years will the account be worth $90,000 if the interest is compounded yearly? Round your answer to the nearest 10. So this is going to be after how many years? That's solving for time. That's what this problem is going to be doing. What you're going to find is that solving for time and solving for interest rate are more difficult. They're more time consuming than solving for principal or accumulated amount. But let's start. $15,000 is invested. So we got P equal to 15,000. It's how much we invest initially. By the way, I look right down here and see compounded yearly, which means we're using the formula with N in it, right? It has to say continuously to use the PERT formula. So we'll be using A equals P times 1 plus R divided by N, all raised to the NT. So we have P. Our interest rate is 5%. So we have R is equal to 0.05. We want it to accumulate to $90,000. So that is our A. We are hoping to accumulate $90,000. That is a lot more money than we have now. We have 15,000. And we know that it's compounded yearly. So if it's compounded yearly, it only compounds one time per year. So let's plug all of those numbers into this formula. We have 90,000 is equal to, our principal is 15,000. 1 plus our interest rate is 0.05 divided by n is 1, all raised to the n is 1, and t we are solving for. That is what we are looking for here. I'm going to go ahead and begin with simplifying this number in here because it simplifies nicely. 1 plus 0.05 divided by 1 is going to be 1.05. 1.05, all raised to the 1 times t is just t. All right, if I want to solve this equation, I am going to need to get the t out of the exponent. And the only way I can get the t out of the exponent is if I get rid of this 15,000 and then take the natural log on both sides so I can bring down the t from being an exponent. I'm going to write that down in words. All right, so there it is. We need 1.05t by itself so we can apply ln and bring the t down. In order to get it by itself, we are dividing both sides by 15,000. Bam, bam. 90,000 divided by 15,000 is 6. So we have 6 equals 1.05 raised to the t. This is where we are applying ln to both sides. Okay. So apply ln to both sides. Then we use the rule that lets us take down our exponents, which is ln of x raised to the c is equal to c ln x, right? That c can come down in front. Bam. So taking ln on both sides, we have ln 6 is equal to ln of 1.05t. The t can come down. We get ln 6 is equal to t ln of 1.05. To get t by itself, I am dividing both sides by ln of 1.05. That leaves us with t equal to ln 6, all divided by ln of 1.05. If you plug this into your calculator and round to the nearest tenth, you're going to get 36.7, and the time unit is years. So it'll take you 36.7 years to change your $15,000 into $90,000 using a 5% interest account compounded yearly. All right. Fun stuff. Okay. All right. Doubling time. This concept that we're about to talk about right now, first of all, only applies, at least the formula I'm about to talk about, only applies with continuously compounding, right? Not that you would get it confused because you're not going to see any problems where that idea comes up outside of continuously compounding. Anyway, this doubling time idea, it works for compounding interest, continuously compounding interest, but it'll also work in our biology section when we talk about population growth, the doubling time for population growth, and it will also have a relevant relationship to radioactive decay when we talk about that later. All right, so how long will it take a continuously compounding account with interest rate R to double its initial investment? And it might feel like there's not enough information here to do anything, but let's look at the formula. A equals PERT. And we're looking to double our initial investment, right? And we're not told a bunch, which is true, right? How much did our initial investment? I don't know. Our initial investment is P. If we want to double our initial investment, that's going to mean that our accumulated value is twice our initial value. Our initial value is P. Okay, P is equal to P. What we're hoping for is 2P. Our interest rate is R. R is R. So really, the only thing we're replacing in this formula is the A. We're going to replace that with 2P. So we have 2P equal to P e to the RT. And now there's a P on both sides, and I can divide both sides by P to get rid of the P. This is totally legal because we're not dividing by 0, so we're okay. Okay. The P will disappear from both sides. And if you're an analytical student, what you're seeing right now should feel kind of like, what? And I'll tell you why it should feel a little bit like, what? What I'm showing here is that the amount of time it takes for your bank account to double in size if it's continuously compounding is completely unrelated to the amount of principal you put in. Look at the P's cancel completely. The amount of principal I have doesn't at all determine how long it takes to double. The only thing that's going to affect how long it takes for our account to double is the interest rate. Right, so I'm going to take and do ln on both sides here. So we have ln of 2 is equal to ln of e raised to the RT. Remember, ln of e raised to the whatever is equal to the whatever. We've said it a million times. It's like the ln e's cancel. So we get ln 2 is equal to RT. ln 2 is equal to RT. The question was, how much time will it take to double? So we're trying to solve for t. Trying to solve for t here. And if you divide both sides by r, you'll get that t is equal to ln 2 divided by r. What does that mean? The doubling time, the time it takes to double your investment, is ln 2 divided by whatever interest rate you have. That's it. That's what it is. Doesn't matter what your initial investment is. ln 2 over r will tell you how long it takes to double your investment. This is an important formula. It also can be rearranged in other ways. For instance, if instead of solving for doubling time here, you solved for interest rate, you would find that the interest rate R is equal to ln 2 over the doubling time. So if you know the doubling time of an account, how long it takes for that account to double, move everything up so I have space. If you know how long it takes for your account to double, you can find out your interest rate from that information. Pretty cool. 2 important formulas. Let's go ahead and use them. Okay. What annual rate of interest compounded continuously should you seek if you want to double your investment in 10 years? What interest rate do we need if we want to double our investment in 10 years? right? So this 10 years thing is our doubling time. We want it to double in 10 years. So our doubling time is 10. We want to find the interest rate. That's this formula, right? The doubling time is 10. This is ln2 all divided by 10. If you plug this into your calculator, you're going to get a lot of decimals. I'm just going to write a few here for a second. Oh man, I forgot to write. Shoot. Round the percent to the hundredths place. Round percent to hundredths place. Hundredths place. That means that your answer should be a percentage with 2 decimals. This is a decimal. We need to convert it to a percentage, and it means the percentage needs to have 2 decimal places. So to convert to a percentage, we move the decimal place over twice. So we get 6.93. That'll give me 2 decimals, 6.93%. So just be careful when you're solving for percent, when you're solving for R, make sure you move the decimal place over because you're giving a percentage. That's it. If you want to double your investment in 10 years, get a savings account that has 6.93% interest. Easy peasy. I could ask the question, how many years will it take for a savings account with 2.75% interest compounded continuously to double its initial investment? Okay, so I have the R in this case. So R is equal to 0.0275. I'm going to use this formula right up here. So this is ln2 all divided by 0.0275. ln2 divided by 0.0275 is, oh, this should say, I don't know, what should we round to? Tenths. Round to the nearest tenth. I thought I fixed this on the worksheet. So this will become 25.2 years. $25.2 years. So it's a really fun, nifty formula that has a lot of relevance. Again, we're going to use this formula again in other ways. All right, so that's it for finance. If you have questions, send me an email. Otherwise, I'll see you in the next section where we start talking about biology applications. Yay! All right, bye.